start.
Yes.
Recording is started.
Okay. So again, once again, a very good evening to all as per Indian time, and good afternoon, whoever, like as per the time. Okay. So I am Dr. Alaka Ponda. I am from Odisha. Currently, I am working as a postdoctoral researcher in Joseph Stephen Institute, Slovenia, and it's my privilege to anchor the meeting on behalf of Association of Indian Physicists and Janardhan Singh Foundation, who has always, like so far, we have tried to reach to maximum students and communicate them with the researchers and faculties, which is our motto, which is Vaigyanika Gyanam. And it's like transcend, sorry, I'm just diverted a bit. So it's like accelerating science and transcending to scientific community. We want to communicate to maximum students, researchers, and faculties all over India and the world. And today's is the first or inaugural talk on WHiP, What's Hot in Physics series. And we will be talking about Chandrayaan-3, and which was like a very interesting and exciting topic in the July-August session of 2023, and everyone was like head over heels about India's successful mission to South Pole for the first time. And we are really lucky to have Dr. M. Shanmugam on this occasion of the talk and the celebration of India's success to moon mission. And to give a brief introduction about the Dr. M. Shanmugam, he has been parallelly working with ISRO, and he is heading Planetary Instrumentation Division section of instrumentation development section of Physical Research Lab, and he has worked many instrumentation facility who has gone to moon and got information which is beneficiary not only to India but to world as well. And we are really excited about the talk, sir. So before that, I would like to request Dr. Sanjay K. Singh, sir, to give a brief welcome to all of the audience here. Dr. Sanjay sir is currently the convener of AIP and is working actively in conducting and communicating and coordinating all the activities that we are doing to reach to students. Dr. Sanjay sir.
Yeah, thank you so much, Dr. Alkama. So on the behalf of Association of Indian Physicists, that is AIP, and Janardhan Singh Foundation, that is JS Foundation, and as a founder president of AIP, I, Dr. Sanj, heartily welcomes you all. And thank you for joining us today. I'm truly delighted to see such a diverse and enthusiastic AIP audience here. It is my distinct pleasure to extend a warm welcome to our esteemed speakers for today, Dr. M. Shanmugam. Dr. Shanmugam, we are truly honored to have you with us. On behalf of Association of Indian Physicists, I would also like to extend our heartfelt congratulations to Dr. M. Shanmugam. Your dedication and hard work, invaluable contributions to the field of Lunar research and the Chandrayaan missions deserve recognition and applause. We look forward to your enlightening presentation today. Thank you once again for gracing us with your presence and expertise. Our mission at the Association of Indian Physicists is to promote scientific awareness and education, particularly in the field of physics. We firmly believe that understanding the wonders of our universe and the laws that governs it is a journey that should be shared with as many people as possible. The role of the AIP is to facilitate and support endeavors like today's lectures, which aim to spark scientific curiosity and expand our collective understanding of the universe. We are committed to promoting the marvels of physics and fostering a deep appreciation for the scientific advancements that are being made. I encourage all of you, especially our younger generation, to actively engage in today's lectures, ask questions, and seek to deepen your understanding of this fascinating field of study. Thank you for being here. Thank you, and over to Dr. Alkama.
Thank you, Sanjay sir, for a brief introduction and informative information. And now I request Dr. Ankit for giving a brief introduction and aim and objectives of the AIP and JSF.
Yeah, in the state of Dr. Ankit, you can call Margi.
Okay.
I
Okay.
appreciate.
Okay. So I request Margi, Miss Margi, to give a brief introduction and aim and objectives of Association of Indian Physicists and Janardhan Singh Foundation.
Good evening, all. Thank you, everyone. Thank you, Dr. Alka, ma'am. Let me just share my screen. Is it visible?
Yeah, it is coming up. Yeah, it has come up.
Yes.
Okay. Good evening, everyone. Myself, Margi Patel. I'm from MS University of Baroda, currently pursuing PhD, and also Gujarat State Chairperson of AIP. I welcome all of you on behalf of AIP family on the first talk under public lecture series, What's Hot in Physics, that is WHiP. So it gives me an immense pleasure to share first the motto and aim of this association. So the AIP is embedded in only one single motto, which states that Vaigyanik Jnanam Vardhayitum Bhautik Shastram, which means that accelerating physics to transcend scientific knowledge. With this logo, we have started our association under such objectives like this association motivates or educates the students as well as teachers and across the country in the field of physics. The aim of this association also is to innovate in physics teaching and in theory and experiments also. It introduces the community to the various physics research fields and allows them to learn from one another's research areas. Then many talented scholars wish to perform good research and maybe somewhere they need more facility or guidance. Through this association, we can help them any time. To provide a meaningful and scientific and academic discussion platform also by providing them various lecture series and talks, etc. So we encourage all scholars and faculty members to explore the interdisciplinary research work through this association. So I would like to brief all of you about the Janardhan Singh Foundation and also the Association of Indian Physicists. So this association is a subdivision of Janardhan Singh Foundation, JS Foundation, registered under MCA, Government of India. And the branch office of AIP is located in Barnala, Punjab. And to increase the outreach of national wide, it is divided into 9 zones, namely north, northeast, east, southeast, south, southwest, west, northwest, and central. And each zone has its respective zonal chief counselor also. Further, each zone is divided into sub branches also. Now, coming up to the WHiP, that is our first talk on what's hot in physics. So this public lecture series is designed to bring scientific awareness to the recent and trending topics in physical sciences. The experts in the field shall be invited to discuss their respective topics. Under this lecture series at the young generation, they shall understand the patience and efforts made to achieve the marvel of physics, and it shall also constrain misinformation about scientific advancements and help people understand the importance of such scientific research. So with this, I welcome all of you to enjoy the lecture series with this Chandrayaan-3. And I would like to suggest that if anyone wants to join our membership, then they are free to contact any of us. We have this zonal and state-wise coordinator, and their contact can be available in the group. So thank you. Over to you, Dr. Alka.
Thank you, Ms. Margie. Now, without getting into much delay, I would like to request Dr. Captain Rituraj Singh, who is our principal coordinator for Association of Indian Physicists. He will be chairing the next session of the talk, and I request Dr. Captain Rituraj Singh sir to give a brief introduction and chair the session. Dr. Rituraj.
Thank you, Olga. So first of all, I take this opportunity to congratulate Dr. M. Shanmugam on behalf of the whole AIP family for the great success of Chandrayaan-3. We also thank him for taking time from his busy schedule to accept our invitation for this talk. Dr. Shanmugam, working as a scientist F at the Physical Research Laboratory, Ahmedabad. He did BE from University of Madras in Electronics and Communications in using. Then he did MTech in Electronics from SVNIT Surat and PhD in Electronics from Dharm Singh Desai University, Nadia. At present, Dr. M. Shanmugam is head of Planetary Instrumentation Development Group and deputy head of the Planetary Science Division of Physical Research Laboratory. So Planetary Instrumentation Development Group is interested with the responsibility of developing several scientific instruments for past and upcoming space missions of ISRO. He significantly contributed to bringing up the space payload developmental capabilities in the Physical Research Laboratory. Since joining PRL, he established the facilities required for the payload activity. His first assignment at PRL was developing high-energy X-ray spectrometer called HEX that was flown in Chandrayaan-1 mission. Subsequently, as a deputy director, he led the team in developing various scientific instruments such as Solar X-ray Monitor XSM, flown in Chandrayaan-2 orbiter, and the Alpha X Particle X-ray Spectrometer APXS, flown in Chandrayaan-3 rover. He also led the team in developing the Adit Solar Wind Particle Experiment SPX for Adit L1 mission. He is instrument principal investigator for several scientific instruments planned for future space missions that are being developed at PRL. For his dedication and hard work, ISRO awarded him with ISRO Team Excellence Award. He has received the Career Development Award from the Lunar and Planetary Institute, USA. Along with all these, he is a reputed Oscar Fellow. In his research career, he has published several research articles in esteemed international journals. In this talk, he will cover the overall design aspect of Chandrayaan-2 and 3 mission goals, scientific experiments on board on these spacecraft, and the technological challenges. He will also brief us about the contribution of the Physical Research Laboratory, Ahmedabad, on scientific experiments on all 3 platforms of Chandrayaan-2 and 3, with the orbiter, Vikram lander, and the Pragyaan rover. In this talk, he will also cover the design and the performance details of scientific experiments developed at the PRL. So, without any further delay, I invite Dr. M. Shanmugam to enlighten us with the expression of Chandrayaan mission. Sir.
Yes. So thank you for your good words. So I also thank the AIP for inviting me to give this talk. It will be wonderful to interact with all the students and all of you as well. And it's my pleasure to be here and then probably sharing my knowledge and experience, whatever I gained over a period of time. So I will try to share whatever I know. It's like kind of ocean. Everything like a space means it's like an ocean. Sciences also is an ocean. So whatever I understood, probably I'll share with all of you. So I will try to share my slides.
Sure.
Are you getting?
Not yet, sir. Yes, sir.
You got it now? The slides are
Yeah.
visible, right?
Yes, sir. Yes, sir.
Okay. So without any further delay, so I would like to kind of briefly talk to you all about general overview of Chandrayaan-2 and 3 missions. So that is the topic which I have chosen. So anyway, thank the Association of Indian Physicists, AIP, for giving me this opportunity to talk to all of you. And before even starting, I wanted to show these two photographs for you all. The photograph which my marker is visible, right?
Yes, sir. Yes, sir.
Yeah. So the one photograph which is from the left side, what you see, it is the photograph taken by our Pragyaan rover navigation cameras, where it has taken the photo of lander sitting on the moon. It is the kind of after seeing this picture, it is like feeling something different. Like we never seen such a pictures by any Indian spacecraft sitting on any planet. So this gave some sort of goosebumps for all of us when we saw this image. So of course, we were all there sitting in mission control system when these photographs were taken. This is the first ones we were sitting there and seeing it when the things were happening as really it was happening. Okay. So the right side photograph, what it's shown here, the picture, it is like a rover, Pragyaan rover moved on the lunar surface. Something like in our early, like when I was student, or maybe many of you also might have seen, when this Apollo missions landed, the astronauts landed on the moon, and their footprints we used to take it as a reference that, oh, something they have done, something like that. But now you can see that our own rover has moved on the moon, and we are able to see these kind of pictures where we are able to do it and achieve what we means. We can also kind of means technologically in kind of in on par with other countries, which we so-called developed countries. So with this, we were able to kind of demonstrate our capabilities to land on the moon, probably the fourth country in the world where we could successfully land on the moon. Soft landing, we could carry it out on the moon. So in this talk, I would briefly touch upon about PRL, because as I understand that there will be many students will be attending this. So I just wanted to give some flavor about what PRL is all about. And then I will try to touch upon very briefly about Chandrayaan-2 and 3, because Chandrayaan-3 we cannot discuss without discussing Chandrayaan-2 and 3. So that gives the basics, where it started, how things have happened, and why we went to Chandrayaan-3 and so on. And then I will try to talk about instruments which we developed at PRL for Chandrayaan-2 and Chandrayaan-3 missions very briefly. And then the technological advancement and challenges. This is the part which always will cover almost in every part of my slide, because the technological advancement and challenges is always the critical issue when you talk about any space programs. So either it may be any science instrument, or in terms of rockets, or in terms of satellites, and so on and so forth. And its impact on the future lunar exploration, of course, I will try to briefly touch upon and then tell you about it. So this is the overall outline of a presentation which I'm going to touch upon in next 45 or 50 minutes or so. So you all may be knowing this photograph which is shown here. He is Dr. Vikram Sarabhai, and he is known as the father of Indian space program. He is the one, he started all the space related activities in India. So in olden days, he has told that the countries have to provide the facilities for its nationals to do front rank research within the resources that are available. And it's equally necessary, having produced the men who can do research, to organize task-oriented projects for the nation's practical problems. So by whatever he said in those days, now you can see that ISRO is more or less doing all these things. Like initially it started with the kind of, we were trying to establish the capabilities with whatever resources we have within the country. And now we are able to demonstrate by means of using or launching the satellites, which is required for the human practical problem, trying to solve the human practical problem. And also with respect to research, carrying out research, we have been part of doing a lot of sending this planetary missions and science-oriented missions, where we continue to thrive on doing this front-end and cutting-edge research in terms of planetary sciences. So probably whatever he told and dreamed in olden days, we are trying to kind of realize it, and which some of them, which you might be seeing it in front of your eyes, what's happening today. And this is few photographs which is shown here. This is the first one where when PRL was started in foundation was laid in 1947. Later, a building was constructed. So the inauguration of that, this photograph was taken. And the right side, this is Sir C.V. Raman Nobel laureate, who was within PRL and interacting with Dr. Vikram Sarabhai. And in this photograph, you can see he is Dr. APJ Abdul Kalam. He is the ex-president of India. He was at PRL in the early days for doing some of the experiments, and then probably learning some of the things what probably he would have used it in the later part of his career. And the other person he is sitting here is Dr. Madhavan Nair. He was our ex-ISRO chairman. He was there. So probably you can see that many of the people who are there are probably some of them also, it's not in the photograph, like U.R. Rao and Kasturi Rangan. They were all kind of initially did their research or started the research work or career in PRL, and probably went on to kind of start ISRO, and now you can see what ISRO is all about. And how it started, the physical research laboratory, you can see that 1947, it is started in a small hut, and then the construction of the small building was started at 1948. And in 1954, you can see that the first one small building came up. That is the old building. It is still there in the front side of PRL. And then in 1970 and 75, there is a multi-story building came up in the behind. So where at that point in time, large number of research activities in different fields have been started. And in Ahmedabad itself, we have one more campus we call Kaltej campus that started in 1980s, where astronomy, astrophysics related activities were started here. And we also have two more observatories there. One is at Mount Abu. It is IR observatory, which is used for observation of all the astronomical objects, which started in 1990, and it started with about a 1 meter telescope. Now we have also come up with a new 2.5 meter telescope that is being kind of finished, and it will be starting sometime soon. Some of the operations will be starting sometime soon. And we also have one solar observatory at Udaipur, that is called Udaipur Solar Observatory. It started in 1981. So probably you can see that we have astronomy related observations which is being done at Mount Abu, and solar related observation is being done at USO, and all other research activities are encompassed in these campuses, which you will see probably the latest photographs of our 4 campuses, which these are the 4 campuses we have it. So, this is the main campus. We call it the PRL main campus, and below one is the Kaltej campus. This is a new building where I am situated, and I work in the space related payload development activities. That is called PRL Kaltej campus. And these are the other 2 campuses which I just now briefed. And at PRL, we carry out fundamental research in different fields. That's what is listed here. One is starting from theoretical physics. We have a geosciences, very strong group of scientists carrying out the geosciences research activity. And planetary science is the one which is started quite late, in terms of 2000 or a little later than that, we started planetary sciences exploration. In fact, no planetary related research, very kind of strong groups were not there in the early days, but after 2000s only we have very strong groups now situated in various ISRO centers, or in fact various universities also people are taking it up. And at PRL we have a strong group which is looking at the planetary research activities. Astronomy, astrophysics, a very strong group is there, along with the solar physics also, and the space and atmospheric sciences research also is being carried out. Along with that, very recent activities like atomic, molecular, and optical physics. This thing is being incorporated to PRL, where we are also looking at quantum-related research activities. So this is the overall nutshell. What is the kind of research we carry out at PRL? And along with that, we also carry out a lot of outreach activities. You know that at PRL, a lot of PhD students are taken for their PhD degree, and in fact, a lot of postdoctoral fellows also come here and continue their research activities after completing their PhD in various parts of the countries. Along with that, we also have a lot of interface with schools, colleges, and various other institutions within India in order to share the knowledge as well as give some sort of courses. And in fact, many people come to PRL to stay some time and spend some time and try to do or kind of start looking at what are the things they can try to do in their research careers. So this is the brief introduction about PRL. And since I will be talking about the Chandrayaan-3 and so on, this space-related activities is not started very recently at PRL. It has been started very long before. Even in 1970s, the things have started. Like this rocket-borne instruments we used to develop at PRL for atmospheric-related studies, and take these payloads and fly it in the rocket in Tumba in olden days. So these are some of the photographs which you can see here. A lot of rocket-borne experiments are being assembled and being flown. And in fact, when we started looking at having satellites, in fact, at PRL, we are started having some science instruments on some of those rockets also, or some of those satellites also in the early days. So this is what has been the kind of history involved with PRL. And to start with, so whenever we talk about any planetary exploration, so any kind of planet you want to kind of study or try to send some satellites to have better understanding of the satellite, sorry, better understanding of the planet. So the primary motivation is that generally we look at how these planets are originated and how they are evolving over a period of time. So this is the main motto of going to any of the planets. Once you have a basic idea and understanding, then you try to understand more about the planet and try to see what are all there and whether any resources are available which can be used for further advancement of our technologies and so on and so forth. So that is the primary motivation. In that, what generally we do is that we try to understand any planet, we try to understand the physical and chemical properties, and some of the physical properties I listed here, which is not hard and fast. So something like a topography, gravity, whether it has atmosphere and what kind of radiation environment is there. And some of these parameters we try to understand about any planet. And similarly, what this planet is made up of, it's kind of chemical composition or mineralogy and elemental composition and so on and so forth, we try to understand. So this is the kind of suite of instrument we have to design to make sure that we try to understand about the planet, what the planet is made up of, what is the environment around the planet and so on, in order to understand its origin and evolution. And for that, we need to have a technological capabilities in terms of the advanced capability instruments, in terms of science instruments, in terms of satellite, which with advanced technologies, and also launch vehicle, which is one of the critical thing where we should be able to launch these satellites, kind of because we have always constrained in terms of launching this satellite because of launch vehicle limitations. We will not be able to, some of the cases like you might have seen in Chandrayaan-2, 3 and so on, like we always orbit, the satellite always orbits around the Earth for a few orbits and keep on giving kind of thruster firing and then try to leave this Earth's influence. So if you have a launch vehicle capabilities, we may be able to go quickly into this planet, so like other countries do. So those things are also very important when you talk about any kind of planetary exploration. And why do we need to go to space? Like you all know that we can simply very nicely sit in AC environment or in a kind of offices, and where you can have instruments and try to observe whatever I was just talking about in terms of physical and chemical properties. That is not practically possible because you all know that Earth is having a thick atmosphere in which a lot of radiation does not come into this Earth surface, where you cannot put instrument sitting on the Earth's surface and try to observe every aspect of the planet. But some aspect of the planet is possible when you are looking at a visible light or maybe these wavelengths, what is shown here, or else in the radio waves, or that kind of wavelengths, we'll be able to see it. But if you want to know more about the planet and in all the wavelength regimes, so you need to go above the space, or specifically you need to go close to the planet. So where you will be able to get very good quality or good in terms of resolution, you will get a kind of very good resolution and you'll have the better understanding about the planet when you can study them in different wavelengths as well. So that's why we need to go to space. We cannot sit in the ground to understand every aspect of the planet. And then it comes to when you are going to the space, when you want to study any planet, so it comes to the space instrumentation. That is one of the critical aspects you need to look into it. So space instrumentation is different from what we handle the instruments in our laboratories. Like that, those instruments we call as COTS, commercial off the shelf instruments. These instruments, what we have it in the lab, will not work for the space environment. Generally, they are not designed to survive very harsh space environmental conditions. Like if you see the space, it is fully vacuum condition. Commercial components will not work because a lot of outgassing issues will be there, and the radiation in the space is very harsh because you get lot of electromagnetic radiation from the sun, and also charged particle radiation from the sun, and also galactic cosmic rays. So all these things will try to kind of destroy the instrument. And also temperature conditions based on which direction you are looking at it. If you are looking at sun, that particular direction will be very hot, and if you are looking at the other side, deep space, the satellite will be very cold. So you have to be also careful, and you should be able to design an instrument which can survive all this very harsh environment. And of course, the instrument also should be having sufficient strength. When you are putting in the launch vehicle, it should be able to withstand the launch. When the vibration happens, the instrument should not break apart. It should be kind of withstanding that kind of vibration. That is very important. So for all these reasons, and also you have the problem with respect to launch vehicle capabilities and so on and so forth, you have to have an instrument which should be very small, very volume-wise very small, and it should be consuming very less power, because in space you have to generate the power by means of using solar panels. So if you don't design an instrument with a smaller power requirement, essentially you may end up putting a larger solar panels that essentially increases the mass. Then it puts a limitation on your overall launch vehicle capabilities. So that means you have to be very careful in terms of designing the instrument which will be able to withstand all the space environmental conditions, and also it should be a smaller in size, lesser in weight, as well as it is consuming lesser power. So these are all very critical aspects we have to look at when you talk of the space instrumentation and compared to the ground-based instrumentation, which we don't care too much about all these aspects. So because of this, the space instruments are generally called one of kind. They are custom designed, and you have to take all this care in order to make sure that this instrument successfully works, survives, and works in the space environmental conditions. And coming to the Indian planetary missions, where you all know that first we started with Chandrayaan-1, and what the slide shows is that these are the list of instruments we at PRL developed for Chandrayaan-1, Chandrayaan-2, and Chandrayaan-3, as well as Aditya-L1 mission. And of course, there are many instruments which will I briefly tell about what are those instruments and all about. And some of these instruments I will briefly also tell more detail about how it works and what is the science goals from these instruments. And not only that, we aim to have some of the planetary missions for Venus and Mars in the near future. For that also, we have been working on developing large suite of instruments at the PRL, which we will be flying it in the future missions as well. And you all know Chandrayaan-1, probably many of you will be aware because these are all very kind of famous missions. So it was launched in 22nd October 2008, and it was inserted into lunar orbit in 8th November 2008. So this had about 11 instruments in total, and high energy X-ray spectrometer is the one where when I joined PRL, I started working on this instrument. And all of you know that this Chandrayaan-1 is a kind of created a milestone history in terms of planetary science, where earlier people used to think that there is no water molecule, and in this mission is the one which has finally found the direct evidence of available of water molecules on the moon. And not only this, though this is first finding and very important finding, there were large number of findings were there in terms of new mineral identification and identification of new small magnetospheres and the small scale ionospheres and things like that. So people have identified on the moon using these set of instruments which is flown there. And also this mission produced large number of PhD students, and they essentially completed their PhD, and now they are all working as faculties in many of these Indian institutions. So that is the one heartening thing to see, that these kind of missions will kind of enthuse a lot of young energetic people who will essentially can work on their PhD problems using these data sets of these missions, and then they can kind of contribute to overall planetary research aspects, which is probably still growing in India, not like other countries where they have reached a certain level. And coming to Chandrayaan-2 and 3, as you all know that Chandrayaan-1 was launched and it was there around the moon for about 9 months or so. And because of some of the technical issues, this mission could not continue for longer time. Though the mission life was expected to be 1 year, and it is survived for about 9 months, and it gave a lot of informative information and some of the findings, new first findings as well. And obviously, when Chandrayaan-1 was there, we wanted to go with the Chandrayaan-2 mission, not just because having the orbiting satellite alone. We also wanted to see whether we can land and then have a soft landing and then have a rover which can move around on the landing site and try to carry out some of the science experiments. So these are the main objectives of Chandrayaan-2. Like you wanted to demonstrate new technology, develop and demonstrate the new technologies, and carry forward the science objectives of Chandrayaan, because any planet, as I mentioned earlier, we need to look at over a period of time in order to understand it completely. So since that was there for only 9 months, and we could get some amount of data to continue to understand the moon in totality, so in a global scale. So we wanted to continue with some of the experiments, in advanced version of some of the experiments which were flown on Chandrayaan-1. So these are the main objectives of Chandrayaan-2. And since Chandrayaan-2 landing did not happen successfully, Chandrayaan-3 mission objectives are more or less same, and it continued to have these objectives of soft landing and conduct rover experiments on moon, and also conduct rover operations on moon, as well as the scientific in situ measurements as well on the moon surface. So these are the objectives. And you all know this slide very well, which is maybe publicly available. Chandrayaan-2, we had something called orbiter, and that is interfaced with a lander. Inside the lander, in this side, the rover sits inside it. So that means the orbiting satellite had a chute of instruments, and a lander which also has some scientific instruments along with the rover, and the overall size, mass, and other aspects are shown here. And what is different from Chandrayaan-2 and Chandrayaan-3 is shown here. So here we did not carry an orbiter that we call as a propulsion module, where it is only been taken to carry this lander till its lunar orbit. That's why it's called as a propulsion module. It only carried a fuel and normal telemetry systems where it can be communicated, and then we can kind of carry this lander till its lunar orbit. And the lander is more or less the lander is more or less same as that of what we flown in Chandrayaan-2, but there is a modification in the overall configuration is there in terms of number of engines used for soft landing. Instead of 5 engines earlier used in Chandrayaan-2, now it has been made as a 4 engines, and the elaborate sensors, number of sensors which were used for soft landing has been increased in terms of providing redundancy and so on and so forth. That's how the lander size also, the weight also is increased when compared to what was flown in Chandrayaan-2. And rover wise, there is no change. It is repeated same what was flown in Chandrayaan-2 in Chandrayaan-3 as well. And when I told you about the Chandrayaan-1 mission, and also when I talked about in my initial slides, generally when we look at the planet, we look at in different wavelengths to study the different aspects of the planet. For example, here, the mini-SAR is a thing which works in the radio frequencies, which looks at subsurface, like a few meters deep into the surface, what kind of material is there. And for example, you take some of these X-ray payloads, C1HXS, which is meant for studying the elemental composition of the lunar surface. So likewise, you have a different set of instrument to look at different aspects of the planet. Otherwise, only one instrument will not give everything about it. And moreover, I also wanted to tell you that the instrument shoot, what we think of flying in Chandrayaan for the moon, will not work for other planets as well. So you need to also have, based on our understanding, present understanding, you need to devise the suite of instruments which is suitable for the other planets separately. Same set of instruments will not work because the environmental conditions around those planets are different. So with respect to Chandrayaan-1 coverage, we had a large suite of instruments, which I already showed you in my earlier slide. And with respect to Chandrayaan-2 and 3, the orbiter had a similar set of instruments, but having a lot of improvement in terms of its capabilities. And Chandrayaan-2 rover, lander rover, and as well as Chandrayaan-3 lander rover, we had some instruments which is there on the lander rover as well. So APXs and LIPs are the one which were there on the rover, and other three instruments, probably I will tell you in the next slide about what are the instruments present on the lander. And this is the suite of instruments which we have flown in Chandrayaan-2 orbiter, where we have a terrain mapping camera, which is meant to kind of study or create a three-dimensional map of the entire moon in the wavelength of 0.5 to 0.8 micrometer with a 5-meter kind of resolution. And other instrument, solar X-ray monitor, which we developed at PRL, and it is essentially a solar X-ray monitor and a class. There is a Chandrayaan-2 large area soft X-ray spectrometer. Together will give the elemental composition of the moon, which I will try to explain you a little later. And IR imaging spectrometer, which is a kind of single instrument which covers about 0.8 to 5 micron in 250 bands, essentially to find out mineralogy and water ice. As you know that Chandrayaan-1 covered only some small portion, and we need to understand the global picture. That's why this instrument was flown again with enhanced capabilities. And we have a optical high resolution camera, which is essentially meant for taking the topography information in a very finer scale, so like a 0.25 meter kind of spatial resolution. Till now, nobody in the world has this kind of resolution pictures which we have taken. And in fact, the images taken by this camera was used for identifying the landing location, as well as subsequently to understand and analyze the issues which we may face during the landing. So this is a camera which worked very nicely for all our kind of landing location assessment and analysis. And there is a SAR instrument, that is synthetic aperture radar, which essentially try to probe the subsurface, water ice presence, and so on and so forth. And this Chase-2 instrument is the repeat of Chandrayaan-1, essentially to again study the lunar neutral exosphere, which was essentially kind of carry forward instrument which was flown in Chandrayaan-1 mission. And dual frequency radio science experiment. This experiment is not a real science experiment. Using some of the communication frequencies, they were trying to find out some sort of lunar ionospheric presence and what is the kind of electron content and how it is varying over a period of time with respect to change in the solar conditions. That is one of the objective of this instrument. Essentially, this orbiter also is planned for 1 year because, as I mentioned to you, the space is very harsh environment, and we have to be very careful what kind of components, what kind of devices, what kind of instrument we essentially develop, and whether it will be able to withstand more than 1 year. So based on our assessment, we thought again we will be able to have this machine with 1 year, but the way it is working after 2019 till now, it is working very nicely without any issues. Some of the results I will show you with respect to our instruments in the later part. And in terms of Chandrayaan-2 and 3 lander rover, these are the instruments which were there. And lander, Vikram lander, we had a 3 instrument. One is called a seismometer, that is, will try to find out any seismic activity which is there on the moon. It can also find out any kind of meteorite bombardment on the moon because it also can create kind of planet wobbling, or sorry, planet kind of, there is a kind of quake on the planet. And this can be identified using this ILSA instrument. And there is a Ramba payload, which again try to find it out kind of ions and electron density near the landing site, near surface plasma. We wanted to try to kind of understand and study, since it has been observed that these things are available or present on the moon surface. And the other instrument is CHASTE, which we call as Chandra's surface thermophysical experiment. This essentially to find out how the heat flow happens in the top 10 centimeter of the lunar surface. Probably in you all will be maybe knowing during Apollo era in the equatorial regions, people have digged about 2 meters and beyond in order to find out how this thermal property of the lunar surface or thermal behavior is there. And but about top layers, they thought that it does not make any much difference. But essentially later people felt that the top surface, the fluffy surface of the fluffy layers only controls this thermal behavior, how the heat exchange process happens. So that is one of the idea why this instrument was proposed and then it is flown. And this PRL, this was partly done and partly done in one of the other ISRO center. And this laser retroreflector array is a pathway experiment from NASA, which we do not have much details about it. And coming to the rover, we had two instruments. One is called alpha particle X-ray spectrometer, which we developed at PRL, and there is a LIBS instrument, which is a laser-induced breakdown spectroscopy. Both are meant to do the elemental composition analysis, but one is a destructive process and another is a non-destructive process. Like a laser one is a destructive process, where if you fire a laser, the sample will get burnt. And in case of alpha particle X-ray spectrometer, we don't create any issues with respect to sample, but each one has its own advantages and disadvantages over other in terms of finding it out the elemental composition. So this lander and rover experiments are designed for only one lunar day, that is 14 Earth days, because at lunar night the temperatures can go as low as about -200 degrees, things like that. So the survival of components or electronic components or many of the materials and things like that used in these systems may not survive when it goes to such a low temperature. That is what probably we faced when we were trying to wake up Chandrayaan-3 lander rover once the lunar night was over, and we could not succeed in it, and as we could not further communicate with the lander and rover subsequently. And you all know that Chandrayaan-2 landing, and there were issues in terms of it did not land successfully, and some of the reasons which analyzed within the ISRO system, and it is already publicly available, this information. Only what was finally felt that whatever the systems we had on board Chandrayaan-2, its ability to handle this parameter variation. That means the dispersion what we get in each of one of the instruments, and the software which is supposed to handle these things. So there we faced the issue at around 1.5 or 1.6 kilometer close to the lunar surface. That's why we could not successfully handle it. And these things were very well understood and corrected by means of incorporating large suite of sensors. In fact, some of the sensors, what we see is the altimeters, velocity meters. We all started having some sort of redundant systems for all of them. And some of these new technologies were tested very thoroughly, subsequently very thoroughly. And of course, in Chandrayaan-2 also it was tested thoroughly, but whatever understanding we had with respect to that, those systems were designed. But whatever data we gained or knowledge we gained from Chandrayaan-2 failure, we could adapt it and then try to carry out more measurements and include more sensors in order to make sure that we successfully land without any, even some system or one or two sensor failures should not have created any problem in Chandrayaan-3 for landing. So of course, all the system worked perfectly and we could land without any issues. So all these sensors, what I listed, has helped in terms of successfully landing on the moon with Chandrayaan-3 or Chandrayaan-3 lander. And in terms of large number of tests, which I mentioned, you can see that there are three important tests we have done. One is that integrated cold test. So all these sensors, whatever we are going to use it on the lander, was successfully tested using helicopter platform, where what kind of the sensor or the performance what we expecting, whether it's giving the same or similar performance, is there any deviations, are there such things were tried to identify using this integrated cold and hot test. So including crane facility also we made at Sherikota, and using these facilities we try to demonstrate all the sensor performances to make sure that it successfully lands. And also lander leg mechanism performance tests, like at close to the lunar surface, it may go at some velocity like about 2 meters per second and things like that. So when it hits the lunar surface, whether the lander legs will survive or some more shock will come to the lander, and whether it will create any issue with respect to the instrument present on the lander, that also has been successfully tested by means of creating a lunar simulant test bed at URSC, where they created the 1/6 of gravity conditions also, and try to test this by means of creating this facility at URSC. So these sensors, what I am showing 9 sensors, these are the sensors. Probably some of you, when landing was happening on 23rd August, so all of you might have seen some sort of line where already a drawn line on that there is a dot which is moving, where the lander position was shown where it is going. So that position is being marked by means of using some of these sensors only to see that it follows the path and tries to see, I mean, the direction it is going and where it is kind of where the position and things like that. These informations are derived from some of these sensors, and it is shown on the TV screens for all of you when it was landing successfully. So this is what it's shown here. Like this is the kind of trajectory which was shown all of you. And using those sensors, this is being kind of real-time plotted where this lander, when it was landing at the particular point in, or when it is going, following this path at that particular point in time. And after landing, like all of you, I was also there in ISRO control system where at Bangalore, and we are trying to, that it followed very nicely, and it kind of, we all felt, so all the sensors were giving proper input and successfully landed. But it's still always we felt that we landed, but we don't have any images to show. But some of these images, what I'm going to show in some sort of movie, where we are sitting, the camera which is there on the lander, which was taking some of the photographs of the moon, which we were able to see at every 32 seconds kind of duration. So that shows that it was going in the right direction, and we are able to see the lander going in the right direction. And what this photograph shown here in this slide is the first photograph taken after landing, about 2 hours later, after 2 hours after landing. So this is the first photograph we saw. When we saw it, we were all sure that the lander successfully landed and without any kind of tilting or things like that. There could be an issue that things could have been different based on how sensors behaved when it is really moving to landing position. So by looking at this picture, so what the image you're seeing here the shadow, that is the shadow of the lander leg. This is the first image we have seen after landing there. And this is being confirmed by, there is a one instrument I talked to you about, OHRC, that is high resolution camera. This is the image taken before landing, that is around 1428 hours. And after landing, this image was taken. That point in time, Chandrayaan-2 was made sure that it orbits around the landing site to see that whether you will be able to see the features of landing. So you can see that there's a lander sitting there, and their shadow is also seen this side. So this confirms once again that it is landed and wherever we intended. And of course, because of some deviation in the overall assessment and sensor performance, the lander landing location was little away from what it was envisaged. The landing site was, as mentioned, it's about 4.4 kilometer into 2.4 kilometer kind of rectangle, but it is landed within that only and little away from the location where we earlier envisaged to land. And the one more instrument which I told you, the SAR instrument, this also kind of did the data collection and try to identify the lander location. And of course, you all know that there are other foreign satellites also shown that our lander is sitting on the moon. So this all gives kind of confirmation that yes, everything went as expected. And these are some of the photographs after landing. It was taken, like this is I've shown you earlier, and this is the one which is the lander camera taking the rover movement or rover measurements, and it is kind of rolling down. And this is on the moon wherever the rover moved. So those traces you are able to see it. And overall, after landing, we continued with our lander as well as rover operations. After landing, all the 3 payloads on the lander has been powered on one by one, and they started collecting the data continuously. And after that, we had taken the rover down, and the rover is moved in multiple directions. Initially, the rover was planned to move like this because the sun will move from this side to this side when it goes from morning to evening, and it was planned like this. But when we went towards this direction, we found a lot of craters and things like that here. And then we again moved and took this direction, where this direction we should safely move, go ahead. Because any crater and all, we go into this, the rover is since a smaller one and will not be able to survive. And if it topples or it gets into it and it does not come out, then probably we may lose that. That's why we wanted to make sure that we move around relatively cleaner area and carry out all the science experiments. So that's how it has been done. And these are some of the first cut results, which you all might have seen it in the ISRO Twitter account itself. These are all first cut measurements. This is not calibrated data, and hence you should not derive any conclusion from these kind of what plots are shown here. And however, a lot of analysis and other things are going on subsequently. And these are only says that all the instruments are working as expected without any deviation, and the results are being analyzed in detail, which probably will come out in terms of scientific publications maybe a short while from now. And coming to Chandrayaan-2 and 3 contribution from PRL, as I mentioned that solar X-ray monitor on Chandrayaan-2 is the one developed by PRL. And the purpose of this instrument is that, as I told you, that one of the important objective of the mission Chandrayaan-2 is to find out the global elemental composition. That means throughout the moon, what all the kind of elements are there and what is its concentration present there on the moon. So for that, the solar X-rays coming from the sun is the source. When it falls onto the moon surface, you get the X-ray fluorescence. And when you detect these fluorescent X-rays from the orbiting spacecraft, you can find out what all the elements are there. And based on the intensity of the fluorescent X-rays you get, you can also find out what is the quantity present there. So, but the quantity or the intensity of the fluorescent X-rays, what you get, we can depend on the material present or the intensity of the solar X-rays. So in order to avoid that ambiguity, we need to continuously monitor what is the intensity of the solar X-rays falling onto the moon. So that's why we need one more instrument called solar X-ray monitor. That means one instrument should look at the sun to study or to understand what is the intensity of the solar X-rays falling onto the moon. And the other one is to measure continuously the fluorescence X-rays coming from the moon in order to quantitatively interpret what is the kind of global elemental composition present on the moon. And this has been successfully done, and a lot of results have come up from instruments together as well as independently. Also the solar X-ray monitor, because it is looking at sun, we are able to do a lot of publications using this data, because this is one of the kind data where you get a very high energy resolution and the high cadence data, which is not available anywhere in the world. This is the first of kind data which is available, though it is from the moon orbit, not looking at the sun continuously because of its own measurement requirements, or Chandrayaan-2 measurement requirements. And in this instrument, we had one of the detector we call as a silicon drift detector. It's a silicon-based detector. It gives the best signal to noise ratio, where we are able to get the best possible energy resolution, where no other detector can give in this silicon technology. So this detector also, we cooled the detector to about -35 degrees to get the best possible performance. As you all know that semiconductor detectors always, when you operate at room temperatures, its leakage current is more, and thereby noise performance will be noise will be more, and thereby signal to noise ratio will be very poor. But when you operate at a minus temperature, it will improve, and thereby you get the best possible performance. And this is the detector which we use in the XSM, where it is available in terms of module. It has inbuilt Peltier cooler in order to cool the detector to about -35 or -40 degrees. And this slide shows the payload or the XSM instrument which we have flown in Chandrayaan-2. We divided them in two packages. One is called sensor package, another one is processing electronics package. And the sensor package, we mounted the detector along with a cap which has a small hole in the center, you can see, which is kind of field of view. It gives field of view of ±40 degrees. As you all know that the sun is kind of which is keep on emitting lot of X-rays. You have a lot of X-ray photons. If you have a large detector, it will simply saturate. The detector will saturate. So in order to minimize the X-ray photons coming to the detector, to make sure that it does not saturate, so we have made a small pinhole aperture which gives ±40 degrees to look at the sun. And it also has a novel mechanism where this was used in order to assess the performance of this instrument on board. Like we carried a radioactive source, small radioactive source, which is sitting in the center, where whenever we want to assess the performance of the instrument, because as I told you that in the harsh environment, instrument can misbehave or anything can go bad. In order to assess the performance, we carried a radioactive source. From this source, the detector will read this X-ray from this source, and then we will be able to identify what is the performance of the detector. This also has two more positions. You see, one we call as the open position, another one is called the beryllium window position. During normal flare conditions, you all know that X flares varies from A-class flare to kind of X-class and things like that. And when the A-class flare, you get only few photons per second, but in case of X-class flare, you get millions of photons per second in X-ray regime where we are looking at it. So when you have it in the normal flare conditions, we keep the detector in the open position till it can reach to M class flare, where the performance of the instrument will be stable with this position. And when the X class flare happens, the photons which will hit the detector will be too much, that will saturate the detector. So in order to temporarily cut off the low energy part for only during that temporary duration, we operate this mechanism on board. This is a kind of we have an intelligence on board, automatically it does, and this brings the barium filter in front of the detector, thereby it cuts off the low energy portion and thereby it handles this number of photons falling onto the detector without any performance degradation. And this slide gives kind of specification and what kind of design we have achieved. You can see that all the numbers what we achieved is much better than what the specification we envisaged, and thereby this is being called as one of the best designed and best calibrated instrument in Chandrayaan-2. That's what we all our kind of seniors who review this overall instrument as well as the calibration and science results, they all appreciate this very well. And one of the important aspects what we have to do always is that whenever you design a science instrument, you need to calibrate very thoroughly. That means you need to understand the instrument, every aspect of the instrument, to see that it is understood very thoroughly. Because when you get the data from the instrument, when it is flown, and when you get the data from the instrument, so how well this instrument, how well this data accepted will be based on what kind of parameters corrections you undertake, and make sure that the corrected data only is released to public. It is kind of consistent with what we expect. So that is very important aspect where we do, and we have done it in PRL, all those things. Once this instrument was developed and it is delivered to a project and it was integrated this spacecraft, you can see that this is the one. Finally, we were trying to see that when all the coverings, everything is done, and we were trying to see that there is no aperture is this kind of, it does not block by anything else, because if anything blocks, then we essentially lose our scientific requirement what we envisaged from this instrument. So that's why we are trying to look at it at the last moment, and this gives some sort of expanded view of this instrument which is there on Chandrayaan-2 orbiter, this XSM instrument on Chandrayaan-2 orbiter. After launching this Chandrayaan-2, so as I mentioned that we had a radioactive source, you can see that performance after launch to till last year we have been looking at it. Now also the same, it is, we are having the same performance. I don't have any recent plot to show you. And the bottom curve, what you're seeing is the flares which is detected by this instrument. You can see that starting from sub-A class flares to X class flare, we detected it. As I mentioned, this mechanism works automatically. You can see that when X class flare happened, the low energy part is cut down from around to 2 kV. That you can very nicely see that it has happened from this instrument. So in fact, this has happened after launch, 2 years after this, only this X class flare we could detect it. And after 2 years, this mechanism also worked very nicely without any problems. And this is the final performance assessment for the XSM. You can see that when the Chandrayaan-2 mission launched, we are in the solar minimum condition. The X-ray flux, what you see is kind of about 10⁻⁹ kind of flux we get it. And now since solar cycle, it is going to the maxima, and you can see that X-ray flux is increasing. So in between the data gaps, what you are seeing is that when sun is not in the field of view of the instrument, or else the satellite is rotated for some other measurements, whereby you will not be able to see the sun. And during solar minimum conditions, we detected large number of microflares, which was not much reported earlier. Earlier, there was a report, there were reports showing some few of microflares and so on, but our XSM instrument detected large number of microflares, which was also reported in some of the scientific publications. And in terms of the performance of the instrument, we have been continuously monitoring. We could see that the last more than 4 years, the instrument is very stable and working nicely without any, not even a small problem we anticipated till now after 4 years as well. And this has been captured a large number of newspapers and so on and so forth in the early days when this instrument was powered on and some science results started coming out. Not only domestically and internationally, also it was covered very widely by a lot of news articles. And also, I wanted to tell you one thing is that this instrument data, XSM data, is being very widely used by a large number of people, including Europeans and Americans and other countries. They have been very widely using this data sets in collaboration with us in and kind of lot of combined studies also being carried out with their own measurements as well. And combined with the XSM and class, this is the kind of elemental maps. This is the first cut results, and of course, there's a large volume of data still available, and that is being analyzed. And these are first cut results where the elemental composition measurements has been already published by class team. And these are some of the results which I'm showing it. Of course, more results are there. I'm just showing it for two results only, where the sodium weight percentage and magnesium weight percentage with respect to measurement is shown there. And now the larger volume of data sets available, we will be able to come up with the near future with the overall global elemental composition of the moon with the data sets we have it. And this data is available in our website, as well as it can be downloaded from ISDC, that is ISRO center, where data is being kind of archived. And interested people can look at it, our website also, any solar events happening, and maybe subsequently they can use this data also if anybody is interested to carry out further research using these data sets. This is one of the unique data set available where people can make use of it for their research work. And coming to the other instrument which we developed, that is called alpha particle X-ray spectrometer. And unless the class and XSM, which gives the global elemental composition, the APXS instrument is expected to give the in situ elemental composition with a kind of area of about a 10 centimeter kind of diameter. That is the area where this instrument looks at the lunar surface and tries to get the elemental composition of it. And in this case, unlike the solar X-rays there on the orbiter producing the fluorescent X-ray, here we are carrying a radioactive source, that is we call it the curium-244, which has both alpha as well as X-ray emissions. And these alphas as well as X-rays keep on bombarding the lunar surface. The red arrows which I'm showing is these all the radioactive sources from which we get to the alpha as well as the X-ray radiation. And from the surface we get the fluorescent X-ray fluorescence, and that we detect again using the detector and try to find out this elemental composition. And this is the mechanical assembly of this package, where you can see that the 6 red points, these are the radioactive sources, and the blue one is the detector, which will essentially detect this fluorescent X-rays. Here the energy range, we are looking at it from 0.8 to 25 keV with resolution less than 150 EV. Here also we use the silicon rib detector, but the design is tuned such that we have a better energy resolution compared to XSM, because in XSM we have a large number of photons. Here the X-ray fluorescence photons, what we are going to get is less number. Thereby our timing characteristics of the design have been changed, and thereby the performance has been improved with that. So that's how we have done this instrument. And this I will not go into X-ray fluorescence, which many of you will be knowing. And one of the important aspects of what we had is that the radioactive source, when we use along the satellite, since it is very harmful for the human being, which we may work around, who may work around this lander, rover, and so on. And this radioactive source, we try to kind of have some sort of graded shielding layers we put in, so that the people working around that does not get impacted. So that is one of the critical things which we have taken care, because otherwise when you put this source or integrate with a lander rover, it will kind of create some sort of harm to human beings working around. So that is one of the important aspects we have taken care. And this is the rover which is shown here, where the AIP instrument is mounted here like this. That means whenever the rover is moving, this instrument will be in stored condition like this. And here, since we are carrying a radioactive source, we also put a calibration plate with carrying 4 metal targets. From this, we can get X-ray fluorescence, try to address any performance degradation happens to this instrument. That is the way this instrument has been designed. And this is how finally the instrument looks like, and it's been mounted like this. And this bigger one size, what you're seeing is mainly because when you are on the moon, you have a different temperature environment. We get the reflected light also from the moon, and also if suppose the rover sees the sun and directly sunlight will be falling onto it, in order to maintain the detector as well as electronics relatively cooler temperatures when such conditions happens. So this kind of radiator plate has been designed, which is part of the instrument as well. And when you deploy the instrument, it will look like this, and it will look at the surface like this. From this to surface, it will be around 5 centimeter, and it forms about 10 centimeter cone kind of thing, where this X-ray fluorescence will be measured, and we will try to identify the elements from that particular area where we are looking at it. And this is one of the sample spectrum we have in our lab. And you can see that with this instrument, this was measured. You can see that all the elements very nicely, clearly you can see. You can easily identify. Of course, after applying the calibration curve into it, we can also find out what is its the concentration of these elements we are having it. That is being done on what are the measurements we already carried out on the moon. And this is the experimental setup we have at a physical research laboratory, where we carried out the calibration for large number of samples in order to have the calibration matrix when we really get the data from the moon, to apply this calibration matrix and to identify the elements as well as its composition. And as I mentioned to you, the last moment before this lander, this ramp, where the ramp is there in which this rover is mounted, before this ramp closing is the last possible operation. And before that, we try to mount this radioactive source. So this is a photograph where we are trying to mount this radioactive source in the last moment, which is captured here. And after the source is mounted here and this ramp is closed, and then it is mounted on the orbiter in order to fly it. So this is the last activity kept because of the radioactive source involved with this instrument. And once this instrument is there on the moon surface, you can see that the video or the photograph taken by the lander imager, where the AIP-WHiP instrument in stored condition, and in this you can see that the AIP-WHiP instrument in the deployed condition for the measurement. And this is the calibration plate spectrum which we have taken, one on the ground, one on the moon surface. You can see that they very well match. We could not see any difference. That means the instrument is perfectly working as it was flown from the ground. And in the right side, which I already shown it, in all these places wherever this rover moved around, we carried out the AIP-WHiP measurements. So in total, there are about 30 measurements we carried out from this instrument, totaling about more than 30 hours of data we collected, and that we have already large amount of analysis has been carried out, and we are in the process of kind of writing a science article on that. That will come out sometime. That probably you all will be able to see sometime soon. And one more instrument, as I mentioned to you, is that developed from PRL is Chandra Surface Thermophysical Experiment. This is essentially to carry a probe which is fitted with thermal sensors when it is inserted into the lunar surface, and it tries to give the temperature profile of top 10 centimeters from the lunar surface. So that since, as I mentioned to you already, this temperature exchange process is mainly, it was thought to be top 10 centimeter only is controlling it. So that is one of the reason why we have flown this. And in this probe also, there is some heater fixed in between. That was to carry out to the active experiment. Like when you insert the probe, only measuring the temperature from the temperature sensors, it will give only the continuous passive measurements, what's happening there. But we also carried a heater. When it heats up, it will also tell that how the heat transmission or heat propagation happens. So when through that lunar regolith medium. So that is also carried out. And after landing, this probe was inserted, and this instrument was working continuously for 14 days, and a lot of data also has been collected. And these data sets also have been analyzed very critically. This is a probe. You can see that on the lander, this thermal probe is mounted like this, and it is in stored condition. When the lander landed, so it is getting deployed, and then it will getting inserted into the lunar surface. And here you can see that in this photograph, the thermal probe Chaste has got inserted into the lunar surface. This is a photograph again taken from the rover imager. So you can see that another instrument called the ILSA, that is a seismometer, which is also sitting there, which is just beneath the ramp on which it is mounted, and that is getting deployed into the lunar surface. And I just wanted to show you one video which gives very quickly about what is the kind of you can just see that this video gives overall view from 30 kilometer landing to, sorry, from 30 kilometer from the lower surface altitude to the landing. It is about 3 minutes video, so just please look at it. So these are some of the images we could see it when the lander was going for landing, which was not publicly available for otherwise other television viewers to see it. as it goes down from 30 kilometer close to the lunar surface. These are the images which was taken. So this is later stitched together in order to make a movie. Though this images are not available continuously because the data was taken for every 32 seconds once. Now you will see that rover will stand and then look at the surface where to land. We have a hazard avoidance cameras which will take the photograph and try to laterally move which place to land based on the craters and things like that. That will come out quickly. Now you can see that rover is stable at some meters height, and then it looks at where to land. And now it is going to land closely. So once it goes close, that is the last image we had. So this is the time when it lands. So after landing successful, this is the image as I showed to you. This is the image, first image we had it. And now you will see the rover ramp deployment. And this is the deployment of the ramp. And these all images we could see live when we are there in mission control system. And now you will see that the solar panel gets deployed, rover solar panel. This is how deployed, and now the rover will pop up and it will come down. So that video will see subsequently. So this is a rover pop up and it's coming down and it moves out from the ramp. So subsequently, when the rover movement and some of those things are also captured, which we kind of put together in terms of video. Now you can see the rover is moving, and now it will be turning to see the sun because we need to generate the power for rover operations. So that was done at the end of the movement. And also, this is the photograph taken by the rover navcam, as I mentioned to you. And subsequently, the rover moving around on the moon. That video also was taken. Now the other video, it shows that our payload APX deployment. You can see that this was happening live. Now it's going back. And one of the experiment what we never thought of doing is that maybe lifting off the lander and see whether we can do that. That is one of the experiment, and the last day we have done it. This was kind of try to see whether we can do some technology demonstration in terms of lifting the lander and then trying to land some other place. So this is what you can see, the engines are getting fired and then it's again landing back. So this was done in the last day of the operations, and you can see that there is a difference before this and after this. There is a difference in locations where it's around about 40-50 centimeters is moved one direction. So that's how it has been done. And this is what we have done. And in fact, if things would have been kind of working nicely, we would have kind of continued to this to lift this lander and try to move somewhere around a few hundred meters away and try to land in order to demonstrate the technology point of view. That was we were trying to do it, but since we could not contact the lander once the lunar night was over and then second lunar day came, we could not contact the rover and we could not kind of successfully do that. Otherwise, we were planning to do that as well. So with this, I would like to end this talk, and thank you all for listening this talk.
Thank you so much, sir. It was a very insightful and inspiring talk. And indeed, it was a very proud moment for every Indian. So the success of Chandrayaan-3. And I believe that from your lecture, our audience would have learned a lot. So it was really very nice talk, and the demonstration, that's how you have sworn, was very good and wonderful. So now it's open for question answer. So we can have few questions. So I think few questions we have in chat section. So can I read it, sir, or can see? So I can read it, sir. So
Yeah, I can also see it. Maybe, yeah.
okay, so I will read it. So,
Okay.
so first question from Nargish Ali. My question is regarding the choice of material of the device instruments, how they exactly test and choose suitable materials under the harsh environment of charged particles.
So means, is it with respect to, I'm not sure, is that with respect to kind of radiation they're talking about, or is it with respect to kind of the charge you get charged because of lunar surface?
Maybe it's radiation, I think.
Probably the radiation, with respect to radiation. Anyway, all the materials what we carry, it can only kind of protect any components or devices up to certain level only. It cannot, the material on which this instrument made of alone cannot protect the devices. The device has to have an inherent capability to withstand these kind of radiation levels. That is very important. Those devices we have to choose accordingly based on the kind of missions we plan. And if it is a long-term mission, accordingly we have to choose. If it is short-term mission, we can plan accordingly. So the devices are chosen based on those criteria.
Okay, so I thought, I believe she would have got her answer. So Ashika Chakravarti has asked. Ashika, you are online, so you can ask. You can unmute yourself and ask question directly.
Yes, sir. Sir, you talked about when you were explaining, you talked about how there is a sensor that can detect all the seismic activities, and also you talked about how it can detect all the meteor bombardments. But my question is, when the rover is on the land, when it's on its way, my question is, how does it protect itself? Like when the meteor is falling, if it somehow falls on the rover, I think that is harmful for it too. Then what is its level of protection that it can protect itself from a meteor? Because when it is sleeping, or what we call it is sleeping, or when we have got contact with it, how can it protect itself? Is artificial intelligence involved in that self protection?
Yeah, so presently there was no mechanism inbuilt on the rover to protect itself from anything. So it is like a first time we are doing things, and we wanted to make sure that we do soft landing and try to move around on the moon wherever possible. And the subsequent missions, you will see that these kind of things would be kind of addressed, maybe taken care at certain level, because in space, like as I mentioned in my earlier slides, space is a kind of very difficult situation where you think of incorporating many aspects to it, you essentially end up making a bulky thing, and then trying to launching is a problem, and you have all the difficulties, as I mentioned, kind of things earlier. So of course, the technology as we grow, so we have to address if these are really the serious issues. Like meteorite bombardment is a kind of no one can control, and it's very difficult also. Suppose if the big rock comes and hits the lander or rover, and you can only design anything to certain threshold. You cannot design for everything, right? So that is practically impossible. So you can think of doing certain level, but it's practically impossible for doing for everything.
Yes,
Like
sir.
if I say that few meter kind of some meteorite comes and hits the rover, it cannot survive in that case, right?
Yeah,
Then
that was my concern too.
small micro meteorites and things like that can come and hit. So it may be able to survive. Those things can be taken care when subsequently we plan the missions if they are really required, and scientifically it is shown that it is required. Otherwise, it may not be as such. So whatever I talked about the seismometer, it can detect any kind of kind of quakes which can happen. People believe that there could be a moon quakes, and there are reports, earlier reports, And because of this micrometeorite bombardment also, there can be some signatures which this instrument may be able to pick up. So as of now, whatever the rover and lander things were happening, this instrument picked up very nicely all the activities which was happening. Like when rover was moving, this instrument is able to pick up. And AIP is getting deployed, that time also this instrument is able to pick up that there is some activities going on the moon. So likewise, we are able to categorize the kind of capacity of this instrument. Of course, something would have happened in that 14 days, since we are looking at data and trying to segregate what is the kind of man-made events, what is the kind of real events that could have happened during those 14 days. We are trying to assess those data sets. So that is going on.
Yes, sir. Thank you, sir.
So there's another question from Ardai. Sir, can you please mention us what distance the rocket has carried the Chandrayaan-3 and from where the propulsion module started its working?
Can you just repeat? I could not get it clearly.
What distance the rocket has carried the Chandrayaan-3?
Okay.
From where the propulsion module started its working?
So it's all the rockets carry this satellite. You all might have seen the videos, right? You have all the liquid engines and solid engines which are there in the rockets. It carries up to only few tens of kilometers in the earth only. Right? So once it goes out of it, it is being taken care by some more stages of the rocket. And at around about 170 kilometers or so, only these kind of engines are used to carry it. After that, satellite, whatever the fuel is there, the satellite only used to kind of control the satellite's orbit and then further to take it to the moon, as well as to capture the moon and revolve around it. So all the fuel and the engines are there in the propulsion module, only used from that at around 170 kilometers till it's reached the moon.
Another question from Gunjan Patil. So what is the difference among our Chandrayaan-3, Japanese SMART and Russian Chandrayaan? What is the success rate according to their ambition? Yes, sir.
So success rate and all depends on how good your technology is and how well you tested and things like that. So the success and all, we cannot compare it with respect to country and things like that. And of course, there are countries which have much advanced technologies compared to India. And what we do is like whatever we do, we try to understand and test to the level which is required, and thereby only the many of our instrument or even launch vehicles and satellite, the success rate is higher because we take care of best possible way of doing everything. So whatever we have, we can do, and what are the capabilities we have it. And with respect to this Chandrayaan-3 Japanese, I think Japanese also trying to technology-wise demonstrate the soft landing and carry a small probe to see if they can land. So that is what I understand from whatever information available publicly. And Russian Chandrayaan, I'm not sure he is meaning when initially Chandrayaan-2 was envisaged. That time Russia and India was supposed to do in collaboration this lander rover. Probably if that is the question, then that time probably it was I can say that it is good that Russians have taken back that they don't want to continue with this project. That gave us a kind of confidence that we can go ahead and develop our own technologies, and we are able to do it. Otherwise, probably we might be lagging few more years in doing all these things. So that is one good thing probably would have happened. From my point of view, I will tell. Maybe others will have a different opinion on that.
So yeah. So other question, can you please explain how water molecules were formed on moon? Have the scientists found the helium-3 on moon?
Okay, so probably I would suggest to them to read a paper published on this subject. What I understand with my limited understanding is that the IR spectrometer instrument, which has, so whenever it detects the water molecule in the spectrum, they get a dip in that spectrum. So whenever there is the presence of water molecule, the absorption is the one they try to detect it. And if that particular wavelength is the dip happens, that signature corresponds to OH or H. That's what I understand. So if there is a dip in the spectrum, that is associated with the presence of these water molecules. Probably I would suggest them to go through that paper for more details, because I'm not expert in that field. So probably they can try to see that.
So then Vishal Kahar, if you are online, you can ask question. You can unmute yourself.
Sir, I
Okay,
okay.
so I have a few questions. So can I ask them one by one?
Yeah,
Please,
ask
please.
please limit your questions. Like there are many
Okay.
questions, so we might have don't much time. So please ask 1 or 2 questions here.
Okay, so first question is that we have plans to go on Venus and Mars. So are there any work? Is there any work going on docking mechanism and fuel transfer, so that we can refuel our satellites in orbit for longevity of this mission?
Yeah, so for with respect to Mars and Venus, these are kind of first time we are going to Mars. Anyway, mission was there, and now presently, when we are thinking of Mars mission, we are planning to go with the lander and rover kind of configuration. It's not that only orbiting satellite will be there. And with the whatever confidence we gained with the Chandrayaan-3, we'll try to incorporate and use it for Mars lander rover. And the Venus, since this is the first time we will be going, we will be mostly going with the orbiter kind of spacecraft only. And there are discussions and plans with respect to having some small probe which can go into the surface and try to see kind of some more understanding about the Venus atmosphere and surface, if it survives, because the temperature conditions are very hot on the Venus. And coming to your docking experiment, there is a plan, maybe sometime soon it may happen. In the space, there is a plan to dock 2 satellites. Okay, it will be launched by the same launch vehicle, and at kind of different means it will be there in the space and around Earth orbit only. It is not like anywhere other planet. So that technology demonstration is being planned, and the work is going on in ISRO, and sometime probably it will happen in the near future. The docking is planned.
Okay, and
More successful, and fuel refilling and all probably can be done, because if you are successfully can dock, definitely that possibility is there.
so yes, that solves my first question. And second question is that currently me and my team are working on a lunar drone, which is based with RCS structures. So we are planning for the lava tube. So how do we go ahead with payload considerations and payload finalization?
So you have to kind of see that whether you are planning to kind of do some image kind of thing, or what is the kind of plan. So like you have to, like a lava kind of thing you mentioned, right? So that essentially you will be able to identify from some sort of images which you can capture. So
Right.
you have to have some high resolution cameras and probably try to carry it and then take continuous movie or photographs and try to assess it. And
So
then
it will be a 12U CubeSat, which we are planning to go for. So there will be one portion for imagery and second for scientific study. So how should we go for that?
yeah, so scientific studies, since you have to once again see the capability of the copter you are thinking of, and if it is like a bigger one, you can think of putting n number of instruments. Like you can even think of putting some kind of SARS, like a kind of instrument where subsurface waters, whether you can try to find it out in other locations and things like that. Presently, it's all concentrated on the polar region. Okay. And equatorial and all, it's there, but it is the less quantity and things like that. So you can definitely have a large suite of instruments which essentially will give more insights of lunar surface and subsurface, compared to having a thing at 100 kilometers, which is not possible to do it. So again, it depends on what is the kind of copter capabilities which is there. And kind of definitely for imaging perspective, you can carry some instrument, and for other chemical and surface properties, you can think of doing some other instruments, which essentially calls for kind of what is the kind of capability we have it. But there can be large suite of instruments which can be carried.
So that solves both of my questions, and thank you for them.
Yeah, thank you. Thank you.
Yeah. So,
So,
yeah,
Omid,
yeah, you can
sir,
ask.
so
Yeah.
first of all, sir, thanks for your fantastic talk, and it was really like in details, and very informative. And I have two questions. So very small questions, and you might answer in 1 minute. So very first question, like in the imaging for the lunar surface imaging, you are choosing a particular wavelength which is like in microwave 2.5 micrometers, or if I assume. So is there any particular reason behind choosing that particular wavelength for imaging?
So the particular wavelength where you can see all the minerals present on the moon, so that most of them covers in that within that wavelength. That includes the water molecule and other things which we just described. So that covers all the minerals which is present on the moon. That's why that particular wavelength was chosen for one of the IR spectrometer. So that is the reason.
Okay, so thanks for the first question, answer for the first question. Second question is way much simpler. So for this X-ray monitor, you are using to manipulate the number of photons which are going to the silicon detector. You are using synthetic aperture, right? You are just reducing the size of aperture. Am I right? So
Yes,
why?
yes, sir.
Yeah, why aren't you using like straight those like a standard quantum optical instruments, like using a polarizer in the half-wave plate to make sure that entire thing is going to the detector just by manipulating the number of photon by using a half-wave plate and a polarizer, or just to cross the polarizer or something like this?
Okay, so I definitely not sure that way it's possible to detect this X-ray photons. I'm not sure. I have not come across that. And if it is there, and there could be other issues which will be there, because this is a standard technique which you use for X-ray photon detection, and this is very widely used also. And probably I'm not sure that the other one polarizer you're talking about, maybe you have to look into it. And I think it may have some inherent difficulties. That's why it is not being chosen. If it can handle the photons, the number of photons which can come from this sun or during different flare conditions, and probably people might have tried. I'm not seeing anybody tried this instrument configuration. I'm not really sure about it.
Yes.
Yeah, maybe if you can be in touch with me, I'll try to find it out, and I can try to.
I think I got my answer, because they're X-ray photons, and these techniques work with very low energies. So, for
Yes,
sure.
yes, it is low energy. Yes, yes.
Yeah. So, this is the answer. So, thanks once again for your fantastic talk, and it was really informative for me and all of other audience. So, also from side of all audience, I want to thanks to you for this really informative talk. But the closing will be performed by those.
Thank you. Okay, thank you. So Dr. Shivlila has raised hand. So Dr. Shivlila, you can ask a question.
Can you hear me?
Yeah.
First of all, congratulations for the successful landing of this rover on the Chandrayaan on moon, Chandrayaan-3. So my question is, how do you control this rover? Means because on the surface of moon it is not smooth as we see in the pictures. So every time, or how you are going to
Your voice is breaking. Dr. Smith, your voice is breaking.
Probably, if I understand correctly, the moon surface is not very even. There are ups and downs.
Yes,
it's possible to have some habitat possibility. That's what your question, right?
Yes.
Yeah. So there's a lot of discussions everywhere about whether somebody can go to moon and stay and things like that. But still, this is some time to go to even think that somebody really can go and stay there, because you know that the environment is not very conducive.
Yes,
it is a vacuum, and you have to produce oxygen for yourself to stay there.
Yes,
and temperature issues and radiation issues. So you have to have a kind of planning for it. And of course, there are people start talking that the top layer of the lunar regolith, which is kind of controlling the temperature flow. Probably with our experiment, we'll have better explanation sometime later, and that will give some idea people are saying that you dig into the surface and try to kind of use this lunar regolith as a kind of protection for things. But those things kind of little far ahead. Maybe we have to think about it.
Okay, thank you, sir. Thank you.
So we have last two questions in our chat box. So Dr. Kirti Batra. So what is the total weight of Chandrayaan-3?
Is this a rover or is it full Chandrayaan-3?
Total,
Okay, actually rover, if you see, okay, weight of Chandrayaan-3 total is about 4 tons. That includes propulsion module as well as lander and rover. Lander rover together around 1.75 tons. So remaining is the propulsion module, and altogether it is close to 4 tons.
Well, I have a small comment here that the weight of Chandrayaan-3 will vary on Earth and on the Moon exactly. Weight depends on gravitational acceleration, so it will really ninth what is on Earth compared to the Moon. Weight actually depends on the gravitational acceleration. So
Yes.
here gravity is 9.8 meter per second square. So
yes.
But that was a funny comment. Okay.
Yeah.
Thank you. So yeah, so another question, Prithviraj RS. Sir, I have got a question regarding its wheel. I assume it's made by molding a single piece of aluminum. How does the rover have suspension on the moon surface? Won't the wheels get damaged as the surface of the moon is very rocky?
Yeah, so these wheels are kind of machined in a single kind of aluminum this material, and in fact the center wheels are made up of some hardened plastic, not even metal, that one. So the 6-wheel rocker bogie mechanism, the kind of configuration was used for 6-wheel configuration was used, and in this there is nothing like a suspension. This 6-wheel configuration itself will kind of negate any kind of of course you cannot you have always a limitation with respect to size and the kind of rover we are having it. So for smaller kind of obstacles it will negate, but for the larger ones anyway we are avoiding it because we are taking images and try to avoid. That's why the rover movement also, when I showed it, it went other direction when we saw that this side a lot of craters and the other things were there. So that you have to do anyway. So you have to do some sort of either onboard fully automated algorithm, or else manually you control the rover by looking at images and things like that. So the second part is the one we have adapted. Like you take the image and try to see which direction to go ahead, where you don't see the obstacles which may essentially endanger the overall rover.
Thank you so much, sir. All the answers. I think Suisa had asked how can we approach for future queries. So I think you can
write emails, no problem. You can write emails. You can call.
Yeah, your email ID.
I have knowledge, so I can try to. Otherwise, I can also guide you to somebody else whom you can talk, and then try to get some idea about.
Yeah, I think so. Last question is in chat box. In ISRO, is reusable rocket is used or one way? ISRO is.
What is trying to say is that whether rockets are reusable or only for launching and then just kind of launch it and then forget like that. And so as of now, all this Chandrayaan-2, 3, what you have seen is the one-time launch vehicles only. So all the things probably you might have seen. I had one more video which showed the rockets also, that all the engines or boosters which will fall apart when it puts the satellite at different altitudes. So that I probably did not show it because that is too long a movie. And it is only one-way launch vehicles. Of course, there are launch vehicles which are being tested for reusable one. And one time it has been done some tests, and that is also being taken as a priority in terms of developing the technologies for reusable rockets. And some of the activity in that direction is being undertaken in ISRO.
Yes, last question. If you can take one last question.
Yeah, please.
Yeah, Soumya has written. Soumya, you can ask.
Yes, sir. Sir, first of all, I'm very grateful for you all for attending this talk. And thank you so much, sir, for this informative session. And my question is that when ISRO has achieved this milestone of reaching the south pole of the moon, and India has become the first nation, the Chinese scientist, he is a very renowned scientist. He is falsely claiming and saying that India has not even close to the south. So when US's Neil Armstrong reached the moon, no one ever said that the US is falsely claiming that he has sent humans on the moon. Then why everyone is trying to point India upon its milestone? And what are your opinions upon it?
Yeah. So, yeah, this I also read in multiple newspapers as well as news channels when it was told. I mean, probably what his point was is that what he thinks is that after 85-degree latitude, only he considered this as a pole, right? So what we said is that pole in the sense we are kind of towards close to South Pole. So it's not like we cannot perfectly say we are at kind of South Pole exactly and things like that. So according to him, he feels that anything above 85 degrees is only pole. So probably he was trying to insist upon that where we landed is not a south pole, but we said that we have given our coordinates where we are going to land, and it is towards the south pole. Okay, we have not said that exactly like 80-degree or 85-degree, 90-degree we are landing. We said that we are going to land around the 70 degrees. We landed there. So probably like kind of, yeah, this is always some people will try to say something more kind of show that they are kind of superior than others and things like that. So it always kind of happens. So we don't have to too much worry about it. What we do, we know, and we will try to do to the best of our knowledge and abilities and achieve what we can achieve. We don't have to too much worry about what others think and others say about it.
Definitely, sir. Thank you, sir.
Yeah, thank you.
Okay, so now I think talk has come to an end. So now I request Dr. Suman to give concluding remarks and vote of thanks.
Thank you so much, Dr. Singh. Okay, so I'll start with saying that it was really informative and inspiring talk, and we really enjoyed it. Okay, so it is my privilege actually to express my heartfelt gratitude to everyone who have contributed to make sure that today's talk is success. And first and foremost, I really extend my appreciation to our distinguished speaker, Dr. Shanmugam, for sharing his valuable and really detailed insight into the kind of technology that goes into Chandrayaan. This is really astonishing for us. I would say your talk is both inspiring and informative. I say it's inspiring because it indeed inspires us, and I'm sure everyone in the audience they really find it more detailed what's are there in the detector and the instrument that is embedded in Chandrayaan. And it is made in India by the Indians, so it is very inspiring for us going forward. I think everyone in the audience will agree with me that Dr. Shanmugam's talk really left us with a somewhat better understanding of the space exploration. So thank you, sir, for your talk. I would extend my gratitude further to organizing committee for their meticulous planning and execution of this event. It is through their dedication and hard work that we were able to gather here today to celebrate the pursuit of the knowledge. I would also extend my thanks to the member and participants for their active engagement. Your presence and thoughtful questions during the Q&A session really enriched the discussion and made this event even more lively. I would give special thanks to Dr. Sonali Patnaik. She is a convener. She is the one who is responsible for making this the talks possible, and she really deserves a deep appreciation for her effort. Last but not least, I would like to express my gratitude to all the attendees who were actually not in person but virtually, but could make it today and join this talk. Your enthusiasm and passion for the physics are what makes our community so vibrant and dynamic. So I would finally like to finish my talk, my vote of thanks by saying that we assume that this inspire us to continue our exploration of the mysteries in the universe and contribute to the progress of the science. And thank you again, everyone, for your participation, and we look forward for future gatherings where we can continue to learn, share, and grow together. Wishing everyone a day filled with curiosity and discovery. Okay, so over to Dr. Singh.
Yeah, actually, we have culture to have a last photo session, so that we missed. So if everyone can switch on their camera, so we can take some screenshots. So
This is the hardest part.
yeah.
Can you keep your camera on for a few seconds?
I was just sleeping, literally, and I just awake.
Thank you so much. Thank you so much, sir, and thank you so much, everyone. So, Dr. Karanda, if you have some announcement to make, please.
Yes, so I would like to, it's the end of the talk and it's a very nice session. Thank you, Dr. Captain Rituraj Singh and Dr. Suman for managing the session. So I would like to conclude by saying that Vaigyanika Jnanam Vardhayitum Bhautika Sastram. That is the motto of our AIP, and I think we would not have asked more information on Chandrayaan-3, and from such an eminent person. I'm really heartfelt. My heartfelt thanks goes to you, sir, Dr. Shanmugam, sir. We are really thankful to you for such a tremendous talk. It was insightful. The discussion was marvelous. And I must say the information that the slides were having must be, it was like some level of space science we are doing, and we are that is some promising things we are looking forward to, and that would have been really motivating to our younger curious minds. And this with this I would like to also mention to our physics enthusiasts that we are looking forward to conduct one informative talk on WHiP, that is what's hot in physics series, and we are looking forward to some interesting topic as well as some eminent speaker to talk about it. And our next talk will be tentatively in mid-November, which will be on Aditya L1 mission, and I hope all of you AIPians to include and join more and more and get the benefit of it. And also I would just like to mention, whoever wants to share your writing articles for our AIP bulletin, please do that as soon as possible. Thank you, and this session ends here.
What is the meaning of
so
this motto? Motto was in Sanskrit and I don't understand. Can you little explain what was it?
So
it is like,
yeah.
Okay, yes, sir.
Okay. So its motto means you need physical knowledge to enhance your scientific knowledge. So like if you want to do scientific in biology, chemistry, everything, you need some instruments. For making instruments, you need physics. So going in any branch of science, you need some knowledge of physics. So without physics, you cannot go beyond certain limit. So that's why, so indeed, scientific knowledge, you need Bhautik Shastra. So that is the meaning.
And what was in Sanskrit?
So that I forgot that.
It is Vaigyanika Jnanam Vardhayitum Bhautika Sastram. That means it's the scientific knowledge. In order to increase your scientific knowledge, you need physics. In like literal terms, that would be.
That's really true. So those are engineers and those want to do the physics. I am weekly doing a physics class. This time it is going to